The Perseverance rover headed to Mars, ready to ride a column of fire and smoke on its way to the red planet.
And liftoff. As the countdown to Mars continues, the perseverance of humanity launching the next generation of robotic explorers to the red planet.
And Atlas TU has gone to closed loop control, standing by for SRB burnout shortly. And we have successful separation of Mars 2020 with the Perseverance rover.
We now have an acquisition of signals, and the years of blood, sweat, and tears from every person who worked on this mission is now realized as Perseverance makes its way to Mars.
Hello everyone, welcome to this month's speaker series hosted by the Mars Robotics Association. We're based in Mars, PA and have FIRST robotics teams for grades 4th through 12th. This month's speaker is Justin Koch. Justin Koch is a robotics mechanical engineer in the Robotic Actuation and Sensing Group at NASA's Jet Propulsion Lab. Justin received his Bachelor of Science in Mechanical Engineering from the California Institute of Technology. During his time at Caltech, Justin co-founded the Caltech Robotics team, developing an autonomous underwater vehicle for a RoboSub competition. Prior to JPL, Justin worked for SpaceX, designing Falcon 9 first-stage structures, and Walt Disney Imagineering, developing animatronics for future attractions. At JPL, Justin's work focuses on underwater robotics research and Mars surface operations. Justin has worked on a variety of robots, from an underwater aquasimian robot arm to an under-ice buoyant exploration rover that was tested in Antarctica. Justin has previously served as a rover driver for the Curiosity rover and is currently preparing to drive the new Mars rover, Perseverance, as well as the Mars helicopter, Ingenuity. Hello everyone, and welcome to Mars, Justin. How are you doing today?
I'm great. Thank you very much for having me.
Yeah, that's good to hear. In this episode, we will feature live coverage of the Perseverance landing, and Justin Koch will be a part of the crew driving the rover once it lands. So, can you tell us a bit about what you do?
Thanks. So I am a rover planner at the NASA's Jet Propulsion Laboratory. So we're gearing up and getting very excited for the landing, where we will be operating the Mars Perseverance rover. So rover planners are responsible for planning out the drives and the arm activity once we're on the surface and ready to operate. So a little bit about myself. I'm a robotics mechanical engineer here at NASA's Jet Propulsion Laboratory. So I work on a whole variety of different robotic systems, both on Earth and Mars. So part of my job is research and development work, specifically looking at underwater rovers. So I've worked on under ice rovers that have gone and explored places like Antarctica or the Arctic to look at how those surfaces are changing and exploring by basically floating on the underside of the ice. I've worked on underwater robotic arm systems for exploring and sampling underwater. But the reason I'm here today and what I'm excited to talk about is rover driving and Mars operations. So I've worked as a rover driver for both the Curiosity rover that's currently on Mars, still exploring, as well as I'm getting ready to be one of the drivers for the new Perseverance rover. Part of my role is also supporting the interface between the rover and the helicopter. So we plan out all of the operations and work with the helicopter flight operations team to plan all the flights and activities of the helicopter. So we're very excited for landing for both Perseverance and the helicopter Ingenuity. So today I will be talking about the Mars 2020 Perseverance rover that we're about to land. So you can see here a simulation of what the rover will look like on the surface of Mars. Some of the goals for this project are essentially looking at the possibility for life on another planet as we seek to explore Mars using the various instruments and tools that we have on the rover. So we have 4 primary goals for this mission. Our first one is looking at the geology of Mars. We want to try to understand both the history and how Mars has changed over the billions of years that it's been there. We also want to try to understand the astrobiology and the interest if whether Mars used to be able to support life. So we want to look at evidence and discover what clues and signs there that can tell us the story of Mars's past. We also have a third objective for looking at sample caching, where we will actually attempt a very ambitious program where we will collect samples and eventually return them to Earth. This means that the rover has a drill that will essentially core and collect a sample, cache it, save it for later, and then a follow-up mission to pick up that sample and bring it back to Earth. And finally, our fourth primary objective is setting the stage and getting ready for human exploration of Mars. We have a lot to learn about Mars, and our rovers are one piece of the tool set for doing that. And so we use these rovers as a precursor to learning what we can about Mars, so that by the time that we have humans there, we know where to look and how to keep the humans safe. Now, as many of you may know, we currently have other rovers that have explored Mars, and our recent one, the Mars Curiosity rover, or the Mars Science Laboratory, MSL, as we like to call it, looks very similar to Mars 2020. Now, that being said, Mars 2020 is upgraded with a whole new suite of tools. We essentially took what worked very well on the Curiosity rover and upgraded it and added some new capabilities. Some of the major differences between the two rover is a whole new set of wheels. So we've been looking at how to best make the wheels robust and prepare for driving on Mars. And we have a whole new suite of science instruments. So on the turret, there's new instruments that will tell us different things than what the Curiosity rover could investigate and explore. And as I mentioned earlier, we have this whole new caching sample approach where we have a whole system inside of the rover that can take the samples that are collected on the turret of the rover, bring them into the rover, cache them, and save them for later. And finally, we have upgraded cameras, 23 total on the rover. And actually, most of them are in color this time. So unlike our previous rover, where only a couple of the cameras were in color, this time we're getting much higher resolution and color images. So we're very excited to be able to share these new pictures of Mars that we'll be collecting. And so with that introduction, I wanted to open it up to see what questions you guys have about our new mission.
Sure. So Susan from St. Vincent Academy asks, what signs of life will the rover be looking for? For example, will there be footprints or fossils?
That's a great question. And really, that's our big question is, did Mars ever have life? And so we will be looking for evidence of past life on Mars. One of the ways that we can do that is looking at the geology to see how Mars has changed. Now, previous missions have looked at that geology and discovered that many places actually had large amounts of water and other resources that could have been places where life could have thrived. And so our new rover will be exploring what the geology and the changes on Mars that took place by using these various instruments. So here you can see we can take close-up as well as far-range images of the rocks for geologists here on Earth to study. But pertaining to that investigation of what life could actually have been supporting, we want to go to places that could have potentially had water or places for life to thrive. And really what we're looking for is not so much fossils, but fingerprints of ancient life. So we want to look at the rocks and the soil to see if there's evidence or clues of this past life. These clues or evidence that we are called biosignatures. These are patterns in the rocks or appearances or different minerals that we can detect that provide evidence that life used to be there by saying that these are patterns that only life-based processes could have created. So it's not so much about finding the hard evidence of it or the fossil, but looking for these clues that tell us about what happened billions of years ago on Mars. some of these patterns that we're looking at come from our different science instruments. So we have an instrument called Sherlock that can look at these different signatures, looking at organics and minerals in the various rocks. So this instrument is mounted on our turret. With the rover, we will bring down the turret and place it next to different samples that the scientists want to measure. We also have Pixel, which is another science instrument, and again, looking at these different elements that are present. And so it's really about looking at patterns in these rocks for detecting places that show that microbial organics could have survived billions of years ago on Mars. So we've done a lot of testing of these instruments here on Earth and looked at the type of evidence that we see in our own fossil evidence, or own evidence on Mars pertaining to these layers. So we're very excited to be able to see what we discover on Mars.
So we know that water is a key signature of life. Odin from Wasatch Elementary asks, was there water on Mars?
That is an excellent question, and that's part of what we are trying to investigate and have been investigating with all of our previous missions. And so really all of the other Mars missions that have been leading up to our Mars 2020 rover have been pertaining to searching for water on Mars. And so we've been looking for evidence of both current and past water. And we've done this both with orbiters that have gone around Mars, landers that have gone into fixed locations on Mars, and our rover program was as early as starting with the Mars exploration rovers and continuing on to Curiosity, and now Perseverance. But what we do know is there has been lots of water on Mars in the past. We've seen tons of evidence that have demonstrated that Mars used to have water just like Earth did. And as we know on Earth, water is one of the key ingredients to life and being able to thrive on the planet. And so we are always looking for places that used to have water on Earth to look for life. And similarly, on Mars, we're looking for those same places that, although they may be dry now, used to have these large lake beds or oceans. And so one of the careful things is when you're landing on a planet like Mars, you have to be very careful about where you land and where you want to investigate. And that led us to an investigation for actually selecting where this new rover would be landing. In 2018, we narrowed it down and converged on our final selection, which we hope to be landing safely on soon, which is Jezero Crater. And we have a short video here that describes why Jezero Crater in particular gives us our best chance of searching for evidence of past life.
This flyover was produced from NASA images taken from orbit. The blue circle indicates the area the rover will likely land. The arcing hills in the center, about 1,600 feet high, and are the rim of Jezero Crater. The central goal of Mars 2020 is to learn whether life ever existed on Mars. It's too cold and dry for life to exist on the Martian surface today. But after Jezero Crater formed billions of years ago, water filled it to form a deep lake, about the same size as Lake Tahoe. Eventually, as Mars climate changed, Lake Jezero dried up, and surface water disappeared from the planet. An ancient lake is a fantastic place to pursue our goal of looking for possible Martian life. On Earth, lakes are filled with living creatures. Evidence of that life is often preserved in the mud and sand deposited on the bottom of the lake. So, we use the rover's instruments to explore the rocks of the ancient lake bed. Here we can see evidence of the former lake. The canyon cutting through the crater rim was carved by a river. As the water entered the lake, it slowed and dropped the sand and mud it was carrying to form the fan-shaped delta. The white line is a path the rover might follow in its first 2 years, called the prime mission. During this period, we use the rover science instruments to analyze the lake sediments. After we explore the delta, we hope to investigate the shoreline of the former lake. To get there, we have to traverse around a sea of modern sand dunes. From this perspective, you can see former shorelines curving around a headland. We can picture waves in Lake Jezero beating on a sandy beach. And finally, we will press on to the crater rim. Jezero Crater formed when a large object collided with Mars, excavating rocks from deep in the Martian crust, exposing them in the rim for us to study. These rocks would have been hot shortly after the impact and may have hosted hot springs. Deposits from these springs would be another target in our search for possible ancient life on Mars.
So as I was mentioned in the video, Jezero Crater is home to this very ancient delta, this water outflow, where rocks are up to 3.5 billion years old. And so we really want to investigate and look at the different signatures that we might be able to see in this region that now no longer has water, but once was full of it. And from orbit, we have been able to collect some data on these rocks and minerals, and we've seen signatures of these minerals that are commonly associated with life here on Earth. And so part of our investigation is always looking back to where we see life on Earth and following that path through Mars.
So even though Mars is within our solar system, it's still a very long way away from Earth. Cooper asks, how did the Mars rover get to Mars?
So it's been a very long journey to Mars, and that's both in traveling there as well as just the time that it's taken to even get ready for this mission to happen. So we've been working on this new rover design and build pretty much since we launched the last one. We've been looking at lessons learned and what changes we might make and new instruments to be included. So it's been a long process with many engineers and scientists looking at how we can design and build this next one, getting it ready through fabrication and testing and making sure it's ready. And then from there, the exciting point, we last year got to launch it in July of 2020 from Cape Canaveral Air Force Station down in Florida and send it on its way on its journey to Mars. And so ever since then, we've been in what we call cruise phase, where we're essentially traveling the distance to Mars, which, as you mentioned, is very far away. And then from there, today we're getting excited to be able to land there and then continue on to surface operations. And so there's a beautiful shot from our launch in July. It was completely nominal, as we like to say, no issues, and it sent us on our way to Mars. We are carried on an Atlas V rocket. As you can see from this simulated image, we pretty quickly separated from it and just pushed the cruise stage that was developed to carry the new rover on its long journey. It was very long indeed, and while it was on its way, we were finishing up preparations and getting ready for surface operations. And that took, about 7 months to get us to where we are today. And across that time, we've traveled about 314 million miles. So a very, very long journey to Mars. But we're excited to be there. And one of the cool things is that we are using a lot of technology that was developed for the Curiosity rover in that landing system that was brand new back then. But we've also added a couple of new features just to make sure we really nail where we're attempting to land. And one of those biggest things that's highlighted here is being able to take pictures as it goes down and actually adjust its course. So the ascent stage will be looking at the pictures of the terrain, and it'll be picking a very nice, flat, safe place to gently put the rover down. So we want to avoid the obstacles such as the large slopes next to the delta, and really just pick a nice flat surface to be able to land onto. But it still takes time to get down to the surface. It'll be about 7 minutes until we reach the ground, so the 7 minutes of terror, as we like to call it. And so during that time, we'll initially, when we have the atmosphere, being able to basically kind of skip down using the heat shield to help brake us, using just the resistance to slow down there. And that'll slow us down from about 13,000 miles per hour, which is what we're currently traveling at, to a much, much slower, but still way too fast, 900 miles per hour. And then we use additionally these parachutes that are very special because they are designed to be going at those almost supersonic, very, very fast speeds there based on the Mars atmosphere there. So it'll slow it down, and then we pop off the heat shield when we no longer need it. And that's the first glimpse that the rover starts to get of the surface there. And as I mentioned, we've got those downward facing cameras. And so when we get the data back, we'll actually be able to see what the rover saw as it was coming in for its new home. After that, we release from that stage, and we have this descent stage that uses these rockets to kind of fly and hover down to the very last few tens of feet down to the top of the surface there. So getting close to the surface. And then we actually just hover there, which, it sounds crazy, but we had to take this special approach due to the rover being pretty much the size of a small car. And it gets lowered down onto this by these ropes, these bridles, as we call them, slowly lowering the rover down onto the surface. So there we touch down, the wheels are deployed, and we gently get placed down there. And then the stage will actually cut and fly away, leaving the new Perseverance rover to go explore the surface. What's crazy about all this is all happening autonomously. The robot has to know, when to trigger everything and have the right sensing and software autonomy that lets it make these decisions on its own. At this point, all we're doing is waiting for the data to come down and see the results. So, this has been really the culmination of all this testing and verification that have gone into making sure that, we're giving it our best shot of a safe landing.
As you've explained, getting the rover to Mars is a very lengthy process. Casey from St. Luke Lutheran School asks, how is it possible for Perseverance to return to Earth with the rocks it collects?
Yeah, so a big part of this mission is getting those rocks that we're looking at back to Earth. This is something that's never been done before. We're looking at the first time that we'd actually be collecting samples from Mars and bringing them back to Earth. Now, unfortunately, Perseverance is going to be staying at its new home. It will be continuing to investigate for as long as it can, but those samples are the key thing that we want to be able to return back. And so it will be collecting those samples with that drill that's on the end of the arm there that you can see in the picture, and preparing them and getting them ready to return to Earth. So at the center of the rover, kind of within its belly, we have a system that we call the sample caching system. So the drill on the end of the rover takes that sample, but then we have to basically stow it in a way that lets us get it safely back to Earth. So we have this whole system that will basically take in the drill and then process it and put it through a bunch of different mechanisms and compartments that verify that the sample's there, check that it's good, and then seal it up and prepare it to hopefully be opened again on Earth. And so it's really about drilling in and taking those samples as a way of being able to do more science on them when we bring them back to Earth. Now, Perseverance has a whole suite of instruments that'll tell us much information about these samples, but it's really not the same as a full entire laboratory that you could find here on Earth. And so in a very important part for looking for possible evidence of life on Mars is being able to collect these samples so that we can use the full suite of tools and laboratories and systems that we have here to be able to really investigate and spend a lot of time analyzing these various samples. Now, a very important part of collecting these samples is making sure that they are kept pristine and that they're not contaminated. So we have this system that basically caches them and seals them so that they are completely sealed from outside. So it's like even more rigorous than making something waterproof, because we just don't want anything to be able to get inside. So we collect that sample, and then we have this whole sterilization process that keeps them safe so that by the time that those compartments are opened here on Earth, we're guaranteed that we haven't exposed them or brought anything that would contaminate our results, because we want only the best evidence of looking at exactly what the rover would have seen on Mars. And so we're very excited about this investigation and being able to use the full suite of tools. So this mission right now is looking at collecting those samples and caching them and storing them up. And then we'll have a future follow-up mission that we are currently in the process of planning called Mars Sample Return. That will be the mission that goes, picks up those samples from the rover and then brings them back to Earth. So it's part of this multi-phase mission process where we collect the samples and then bring them back. So this is part one of a chain that will enable us to learn even more about the surface of Mars by bringing these samples back.
So a lot of the rover's actions are autonomous, but scientists back here on Earth still have things to do. John from St. Mary's School asks, how do the scientists on Earth control and do the experiments on Mars?
That's a great question, and that's what we're gearing up to begin, which is our surface operations. So the main way that we talk to the rover is through a network of satellites and dishes on Earth that we call the Deep Space Network. So Perseverance will be communicating through this Deep Space Network, which has these very large dishes spread out across the Earth. We have one in California, Spain, and Australia. And across those 3 points, we get full coverage as the Earth rotates. So we can always be talking to the rover, even if it's we're facing away from Mars here in Pasadena. And so all those communications route through this facility here at JPL that then relays the data back so that our surface operations team can analyze it. We also rely on orbiters that are on Mars that relay information back. So the Perseverance rover will talk to these orbiters, which then basically save the memory from the rover that's being transmitted, and then relaying it back to Earth when they come in sight. So that's kind of our way of being able to relay back information to Earth. Now we do have a slight delay depending on where Mars and Earth are in their orbits. It can really take anywhere between 5 and even beyond 20 minutes for those signals to transmit. Sometimes even when the Earth is and the sun is in between Earth and Mars, we even have periods of time where we can't communicate with the rovers. And so we typically will plan on a once a day basis or once a sol, where we plan a full day's worth of activities. We send it up to the rover, and then as the rover is executing it, we in the operations room go to sleep, and then we wake up, get the new data set downloaded of what the rover did. The rover takes a nap because it's nighttime on Mars, and then we proceed with our planning. And so we have a full plan ahead for the new rover once we land. And so we'll be operating on what's called Mars time, where we will be syncing our clocks with how the rover is sleeping, so that we can make sure that every single day that we have on Mars, that we'll be able to operate for that initial window. So the first few months, us in the operations room will be taking basically sleeping just along the clock of the Mars time. And so that means every day we essentially stay up about 40 more minutes later and then sleep 40 minutes in. So we're always shifting our clocks relative to the rover. And so our prime mission is about 1 Mars year, and so that's roughly 2 Earth years. So that is the period of time that we're going to be pursuing our primary objectives that we've touched on, and then from there continuing on to further investigations like we have with all of our other rovers that have continued on past their prime mission. And as I mentioned earlier, we have a lot of cameras on this rover, and those are the main way that we get information back to see what the rover can see. And so it's got in its what we call the mast at the top, it's got very high resolution, what we call Mastcam Z, so they can even zoom in. Or we also have nav cams, which are a little bit wider field of view and give more context. We also have our what we call HAZ cams, so we can see what's directly in front of the rover or behind it, kind of like our backup camera, like on a car. And that lets us see if there's any obstacles that are near our wheels that we want to avoid. And we also have a few cameras on the turret, the end of the arm as well, that can go and zoom in and take very close-up shots of what we're trying to investigate. Many of these cameras, it's very cool, are even available in 3D. So we can put on 3D glasses, and because we have two cameras that are placed a little bit apart from each other, we can see in what's called stereo vision. So we can be able to put those 3D glasses on and give context. And, it is actually very helpful for us to be able to see what the terrain might look like, the slopes, because it's very hard to drive with one eye. So it's nice having that 3D vision for the rover. And we'll even be recording video and pictures as we do the landing. So we're very excited to be able to see those as well. And we're using those pictures both for the science, but also for the navigation as well. And so we can get these broad context shots of where the rover's located and be able to plan our drives accordingly. And then, as I mentioned, we have this capability to basically zoom in, and it's really like holding a magnifying glass that a geologist might have while investigating rocks on Earth. But the rover uses this zoomed up camera on its hand to be able to go very close in and look at the details of the rocks to learn more about what we're trying to investigate. Unique to this mission, which hasn't been done before in previous rovers, we actually have microphones. So for the very first time, we're going to be able to hear what Mars sounds like. So that's another area that we're very excited to be able to get that data down to and be able to hear what the rover hears. And we also have these instruments that let us use the arm and drill to look at rocks. And so this image here shows the arm. It's pretty strong. It can basically do a bicep curl at the end with this very massive turret on the end. So we have this very beefy arm that lets us place it wherever we want in the workspace. And that really gets our science instruments as close as possible to wherever we want to be able to investigate. And as I mentioned earlier, those mass cams let us zoom in and see really far away. And so we can get very accurate shots of things that are maybe too far for the rover to travel to or off in the distance of somewhere that we wouldn't be able to drive up onto. We also have a laser that's on what we call the super cam, and that lets us zap these rocks. And so as they get zapped, they release particles and emissions that basically let us learn about what that rock is just by that laser. So it's pretty cool to say that we have this laser shooter on the rover. And then similarly, we have the Sherlock and Pixel instruments on the turret that are the actual instruments that go down and look at those close-up pictures or looking at those different biosignatures that I talked about earlier. We also have RimFax, which is essentially a radar that shoots down and lets us see the geologic features underneath the surface. So we can investigate what's underneath the rover without even having to dig under it. So we can use radar as a way to learn more about the topography and the features that are underneath the surface. And of course, like any good rover, we have a weather station that lets us learn about the wind speed, the temperature and the humidity, and basically what the environment is like, so that the rover can understand how that changes as it travels around and as the day and night cycles there. So as I mentioned, we have this whole suite of science instruments and tools that let scientists basically have the best chance of learning about the surface of Mars without actually being there. And so we collect all the data with these different tools and instruments, and then we download it. The scientists will analyze it, and then they work with our team of rover drivers and the whole larger operations team that's also looking at everything else related to the rover. And we plan up how we want to execute and what observations we want to take for the next day. So we create our plan, and then we send it up. So it's really kind of a once a day, or as we call in Mars, a SOL, which is a Mars day, once a SOL day, where we plan, send it up, the rover operates, and then it goes to sleep. We get the data down, and then we proceed. And so we continue on the cycle to basically investigate and study, just like scientists would do on Earth in these investigations. But of course, being able to deal with the long communication delay that it takes to get to Mars.
So you mentioned the Mars rover has quite the itinerary. Miles asks, how does the Mars rover get to these different areas on Mars?
Yeah, so we travel to each new location by essentially planning where we want to drive to. So we have a whole suite of tools that we call the rover planning tools that let us simulate and visualize how these drives might look like. So as you can see in this picture here, we can actually create a map of images that the rover sees so that it can recreate the terrain that's underneath it. And then we use this tool that lets us in 3D visualize what it might look like for the rover to drive over that terrain. So on the right image, we have this simulation that shows a simulated rover driving on the images that we collected. And this lets our team, the rover drivers, use these tools to be able to simulate and test out these drives so that we can plan the best drive to get to where we want to go. It's important for us to make sure that we're not going over any terrain that's too difficult for the rover. So that's things that are very sandy and slippery that you might be able to get stuck on, places that are too steep, very high slopes that the rover wouldn't be able to get up. And so we want to plan a drive that's safe. And so by using these visualization tools, we can do that by essentially looking at what the rover sees, planning out those drives. And so we work with the science team who helps us figure out where we want to drive the rover to next. And then we use these tools to navigate and plan around. In many ways, it feels like playing a video game where we're sitting there and planning out these drives, making sure we avoid certain rocks. And then once we're happy with the plan, at the end of the day, we send it up to the rover to be able to run the next day. And so these tools then let us basically map out areas. So as you can see on the right, we have places that we can say, don't drive there, that's not safe. So we can tell it, give it kind of waypoints to travel to drive. And so we can see those simulated paths and being able to tell the rover, make sure to avoid those areas. But the rover also has some other features too. And so by the end of the drive, we can take a picture that gives us basically our first information about the drive. So what this picture is showing is a view from those hazard cameras, but this is from the Curiosity rover. What's special about this picture to me is this was actually the first drive that I did on Mars. When I was training to become certified for a rover driver, I had planned out this drive where we essentially drove to this patch of sand that we want to investigate, and we did a little pivot with the wheel to be able to move some of the sand out of the way that we could then investigate the next day. But we planned out this whole drive. We simulated everything, looked good, and we sent it up. And of course, we went home, went to sleep, and it was very, very nerve-wracking. But of course, came in the next morning, and this was the first picture that we saw. And so, for me to see a picture that the drive had worked flawlessly and that we got the data that we expected, it was a very surreal experience. So it's very fun to send these plans up and then wait until the next day when you get the data down and see what happened. But besides having the humans tell the rover where to drive, we also have some onboard capability for autonomous navigation. So the rover can take images and basically analyze them to figure out where is safe. So this is showing some of our capability from the Curiosity rover that's looking at the terrain, and it's creating this 3D map and showing the green areas that are safe, where the red areas that it wants to avoid. And it can plan out the paths for it to take. And so it's always creating this map here where it's creating these different cells saying how safe it is to drive on the different areas. This is nice because it lets us drive in places that we haven't seen yet, so we can drive even farther than the cameras might be able to see. On the new Mars 2020 rover, we actually have upgraded this capability, so it's faster than ever. And so we're expecting to be able to double or triple even the distances that we might have been able to travel with the Curiosity rover on one day. So we're hoping that this then enables us to get even further and faster and be able to cover much more ground than we were with the previous rover. And you can see here, this was one of the autonomous drives that we did with the Curiosity rover, where we said, we want you to get to this goal finish line here, figure out how to do it. And you can see it kind of took this turn that avoided some rubble that it was a little bit nervous about because it thought that it might be dangerous for the wheels to grind on. So it picked a path that kind of threaded in between those two areas there. So we used this whole suite of tools from the autonomous driving modes to the human modes to work with the scientists to figure out where they want to go. And then we plan these different drives that hopefully gets us as close as we can to those objectives.
Mars is not as hospitable as Earth, so Asher asks, how is the Mars rover going to survive?
Yeah, a big part of surviving on Mars is making sure that we have power for the rover to run. It doesn't run on gas or anything like that. It actually runs on electricity. We have a battery charged a generator that produces heat from the radioactive decay of an element that's inside the rover. That is always helping make sure our batteries stay charged. It's nice because it means that we don't have to rely on the sun for solar power like some of the previous rovers. So we can even survive in storms that might cloud up the entire sky because we get all of our power from internal. It's about 100 watts, which is only a bit more than very bright light bulbs. So it's a pretty small amount of power that is always charging and keeping and maintaining those batteries. So we make sure to put the rover into naps occasionally so that it can save power and then use that power for our different observations. Being a rover, a big part of exploring is also the wheels. So on the left, you can see the Curiosity rover. And a big part of this mission is we actually learned a lot about Mars and the different type of terrain by our previous rovers. So one of the things that Curiosity discovers is that Mars has very sharp rocks. We saw these, the rover drivers, we call them can opener rocks that are just very pointy and sharp and just cemented into the ground and the perfect size to stab at your wheels. And so we developed a number of holes in the Curiosity wheels. Now, they're still running and we expect them to continue on with many more years of life, but they degraded at a rate that was faster than what we had originally expected. And so we took all those lessons learned and built these new re-engineered wheels on Perseverance that are much more beefy and strong and able to survive even the toughest terrains that Mars might throw at us. So one of the things with these missions is we're always learning and taking those into account to make sure that we have the best chance of surviving. And so this new rover took all those lessons from all of our previous missions to give us our best chance to hopefully continue on as long as we can.
In preparation for these expeditions, we know you guys do a lot of testing on Earth. John from the University Scholars Program asks, what robotics are being tested on Earth right now for use in a future Mars expedition? Is it true that the visionary work for this effort started 35 years ago?
That's right. We are always investigating here on Earth things that we can learn about these robots before we even plan to send them to Mars. And so we are thankful for a long history that we have here at JPL of exploration of Mars with these different rovers. And so you can see here our kind of a family portrait of previous rovers that have really paved the way for our Perseverance rover. So on the bottom left there, we have Sojourner, which was our very first rover, about the size of a microwave. And it was sent on as a what we call a technology demonstration. It was an experiment to see what it might look like if we put something that moved onto one of our existing Mars landers. And so we learned a lot about all the new science and capabilities that you could do with rovers. And so we said, well, let's send a whole mission that is a rover, and that graduated onto the Mars exploration rovers that were solar panel powered. And then we continued on through the Curiosity rover and now Perseverance. So it's been a long history in the making of these systems and tools that let us explore Mars. And as you can see with the people in the center of this image, these rovers are quite large. The Curiosity rover and Perseverance rover are about the size of a small car. So these are pretty massive and have a lot of capability on them. And so what's important to do is all of this testing to make sure that before we send these very expensive systems to Mars, that we've really done our homework and made sure that they are ready for the terrain there. And so we have at JPL what we call the Mars Yard. So it's basically a playground that has features that a rover might see on Mars. It's got slopes and rocks and holes and any type of feature that we would want to make sure our robots are robust to, that we can experiment on. And this rover that's on the right here is called Scarecrow, which is essentially a version of the rover that's the equivalent mass. So because Mars has a lower gravity, by having a robot that has less weight, that lets us simulate kind of the same contact pressure and dynamics that a Mars rover would see. And so here we're testing as it drives up the slope. On the left, there I am planning out our commands for this test bed that we have. We essentially have a copy of the rover on Earth that we can use for simulating and verifying our commands and very complicated procedures before we send them to Mars. So we have a full suite of either software simulation or even simulation on actual hardware to make sure we're ready to go before we do these different types of maneuvers on Mars. So I spoke about technology demonstrations, and we're very excited to have one of these experiments on our current rover, which is looking at a helicopter on Mars. And so integrated to the belly of the rover, so this is the rover but upside down, you see one of our engineers actually mounting the helicopter. You can see those carbon fiber blades sticking out and stowing it in preparation for its journey to Mars. And so this helicopter, it's called Ingenuity, and it will demonstrate the first powered flight on another planet. So using a extremely light body and these large carbon fiber blades, it will spin them around extremely fast and generate lift. Now, Mars has about 1% of the atmosphere of Earth. You get a little bit benefit of having the lower gravity, but that's like flying a helicopter here on Earth at 100,000 feet, which is way, way higher than we normally fly helicopters. And so we had to re-engineer some of the different approaches that we're taking with the helicopter. There's also a whole component of the operations of how do you communicate with these different systems that are all operating independently and making sure it's safe, right? We can't have the helicopter flying close to the rover, and we have to ensure the safety of that. So we have a short video here to show that highlights how we're going to do this technology demonstration. So this is the Mars helicopter. So it starts off stowed underneath the rover. We'll actually deploy it so it's vertical and then drive off of it. We have to be careful to drive off enough that it'll have time for its solar panels to charge, because this is a solar powered vehicle. After that, we make sure we're a safe distance away, probably about a football field or so. And then we will actually power up, spin the blades, and perform the very first flight on another planet. And so the helicopter is able to fly a few meters up off the surface there. And the rover will actually watch along. So it'll be taking pictures and trying to get a shot and view how the helicopter is flying, as well as the helicopter sending data back to the rover. So you can see these pictures here that it's taking, looking underneath it. And that is actual images that perhaps someday a future mission could use to send a helicopter scout to look ahead to where the rover might plan to drive, make a map, and that lets us safely navigate over it. So this is an experiment. We are looking at if it's possible to do this flight. We've done all of our analysis and homework, and everything looks like it's possible. We've done testing in the vacuum chamber, but it's not until we get to Mars that we can really prove and demonstrate that this is capable. And so by doing these first kind of experimental flights, we hope to pave the way for what future Mars explorers might look like, and how a helicopter system that has science instruments might be able to explore in a different way than rovers. So we are always looking at new technologies and experiments as a way to learn more about Mars. So we are very excited to see how this helicopter technology experiment might pave the way for even future missions to Mars.
So the data we get back from this Mars rover will hopefully provide us insight into future expeditions and also possibly colonizing Mars. Ben asks from Butler Intermediate High School, how many years do you think it will be until people can try to colonize Mars?
So a big part of this mission is being able to pave the way towards future human exploration of Mars. Now, we've never sent people there before, but before we get there, we need to do a few preparations to make sure that we are ready to send people to Mars. And so this rover itself will be demonstrating some of those key technologies that astronauts would need before we are able to safely plan a mission there. Mars is very challenging. It is extremely inhospitable. It's even worse than places like Antarctica or the top of Mount Everest that are places that we have challenges to this day of maintaining populations on there, let alone they are very dependent on the supplies that we have here on Earth. For us to send and eventually colonize Mars, we would need to be able to demonstrate that we can sustainably live on this planet that is extremely cold, has a very thin atmosphere, and doesn't have the same capability for agriculture that we do here on Earth. And so we need to use these technologies as a way to be able to support a life and sustain it there. So before we can even colonize, we need to send people there first. And this will be one of our next future steps for eventually sending humans back to the moon as a way to get to Mars. And so we're hoping, within, of course, our lifetimes of being able to send people there soon. So in many ways, it's important to learn about the history of Mars and the origins of it and what materials are there so that we can use those materials to be more sustainable and be able to use the local in situ or the resources that are there on Mars to be able to support humans. So the part of the rover that's investigating what the geology and minerals and materials that are there is an important precursor to that. As well as we have another technology experiment that we're excited about, which we call MOXIE. So MOXIE is looking at if it's possible to generate oxygen for humans in a sustainable way on Mars. So we're looking at basically a method for this instrument to convert carbon dioxide from Mars's atmosphere into breathable oxygen that we can use to sustain life. So this is an instrument that's mounted on the Perseverance rover that we'll do a few experiments with to be able to demonstrate that, yes, it's possible for us to take that carbon dioxide, convert to oxygen that humans can eventually breathe. So this technology is a precursor to then a technology that would support astronauts living on Mars for a brief mission, and then hopefully progressing to having a human colonization. So I think we're still many years away, but we're taking those steps now so that hopefully it can be sooner and possible to support our have people on both Earth and Mars.
So I've heard you've been on youth robotics teams before. How did that help you with your current position?
That's right. I was very fortunate to be able to be participating in these various robotics teams since a very young age. I started with the Lego kits and playing with those, and eventually that sparked my interest in engineering. And in middle school, I joined a team for the first Lego League. So this was using these Lego robotics kits to be able to program them and compete in various competitions. Had a lot of fun with that and progressed on to FIRST Robotics in high school, where we built these different robots to compete in the FIRST Robotics competition. And it was a really great way of sparking my interest and being able to discuss these ideas about robots and just see what's possible for careers and opportunities in the various engineering areas. And so I was able to get my hands dirty and work with the different machine shop tools to build these robots, programming, and just exposure to all of the different skills and aspects of engineering. And so that was a big part for me to then pursue mechanical engineering in college. And even in college, I continued on these student robotics teams. I, as a freshman at Caltech, discovered that they didn't have a robotics team, which was crazy to me and some of my friends. And so we ended up starting one, which continues on to this day. And it is a team that just builds robots to compete in various competitions that we find interesting and challenging. And it's just a great way to develop these skills and be able to pursue interests and be able to talk to people that have careers in these areas and learn about what goes into the daily life of being an engineer. And so I highly recommend participating in these different activities for anyone that's even interested in science, technology, or anything related to those fields. I have a number of friends that competed in these, and they didn't necessarily continue on for engineering, but they took those skills that they learned and were able to be very successful in whatever careers they chose. So I'm very thankful for all the opportunities that I've had in these different student competitions, and I really also am thankful for the mentors that I had. They were exceptional people who could provide both all their time and volunteering effort to support our student teams, but also just giving perspective about what it's like to have a career in this area.
Amy from McMurray Middle School asks, as students, can we help in the investigation?
The answer is definitely yes. We are very excited to be able to share what we're learning and our investigation on Mars with the public. It's one of the nice things about NASA is, we are entirely publicly funded thanks to taxpayer dollars. And so we share that information and all the images that we collect with the larger community. So you don't even have to be a scientist. Anyone can download the data that we're collecting and see the images. So once we land and have that information available, absolutely be sure to check out our different places where we'll be posting pictures. So you can go to our Facebook or Twitter or our main public outreach website and be able to see the pictures essentially as we get them from the rover. And even besides the pictures that we post on social media, you can just go to our raw photos and see the pictures that come down from the rover as we get them. So there's always opportunities to be learning about the science that we're looking at, the new investigations that we're doing, we'll be publishing. But one of the areas that we're really excited about that I have been talking about is that sample collection. And what's particularly interesting is, we have this different mission concept phase for this is the rover that will be collecting the samples. And then we've got Mars Sample Return, which will be bringing them back. What that means is the scientists that will be investigating and looking at these samples are probably still in school right now. Some of them may be even just starting elementary school. It's a number of years away, but it's very important that we maintain that this is going to be available to this next generation to be able to explore. And so these samples are going to be a key part for learning about Mars and its history. And it's those scientists that don't even have their degrees yet, but are just interested in science to be able to pursue it. So if you're watching this and you think that Mars is really cool and that you would love to be one of the first people to look at a Martian rock sample, that very easily could be you. Work hard in school, pursue your higher education, and just stay curious. And you too might be one of the first people to look at what a Mars rock sample looks like in person.
So we are almost out of time, but one last question to wrap things up. Throughout your life, what is the best piece of advice that you've ever heard or received?
The best piece of advice that I've received and tried to follow is never be afraid to try challenging things. It's very easy to see something that looks difficult, and think that couldn't be you, or it's not something that can be done. But all too often, it's this idea of failure that we're afraid of. But really, failure is a way of learning or being able to change how you approach things, to take a new stance and be able to come up with new ways of really succeeding. And so I always encourage people to try difficult things or things that you might not have seen yourself doing, but helps you grow and get better at what you're trying to pursue. At JPL, we certainly always try to do things that are extremely challenging and sometimes do have failures. We have a saying, and it's a saying that I really love, dare mighty things. At JPL, we really try to look at what the future is, what the very challenging, hard engineering tasks are, and we pursue them, because even if we don't succeed every single time, we're always learning, always changing our approach and making things better. And so for us, it's really about looking forward to how we can just continue to push and try new things so that we can continue to change how we learn about both Mars and the solar system, as well as our own planet.
Well, we know you need to go drive the rover now. So thank you for the great advice and for joining us today.
It's my pleasure. I was very happy to be here.
Once again, thank you to everyone watching and to those that submitted questions. Join us next month as we get ready for Earth Day and talk with our guest, Mandy Revak from the Pittsburgh Zoo and PPG Aquarium. The Mars Robotics Speaker Series is a production of the students of the Mars Robotics Association. Mars Robotics is part of FIRST Robotics, with teams competing in FIRST LEGO League and FIRST Technical Challenge. For more information about the Mars Robotics Association, the Mars Robotics Speaker Series, or any of our other programs, please visit us online at www.marsroboticsassociation.org. We will now join NASA's live coverage of the Perseverance landing, already in progress.
Close enough.
Now, Rob, you've been right where the Perseverance team is sitting now. What's in store for them as we approach landing?
Well, this is the nail-biting time. Fortunately, we still have ones and zeros coming, but very soon, as we approach cruise stage separation, the transmitter on this rover we've been using all the way to get to Mars is going to be turned off. So we will lose our ability to see ones and zeros. But the good thing is, once the cruise stage is gone, there's another radio that will continue transmitting a tone, so that like a flashlight, that will allow us to at least see that the vehicle is still on, and that color of that flashlight tells us a little bit what state the rover's in. But soon after that, it won't be very long before we'll be able to hear more ones and zeros coming from the spacecraft. So this is a really exciting time, and it's just important to remind people there's a lot that can go wrong in a day like today. There are thousands of things that have to go right.
Yeah, we had success in the past landing on Mars. You'd think it gets easier, but it really doesn't. Why is it still so difficult?
Well, because it's involved thousands and thousands of things, hundreds of thousands of lines of code. There's 79 pyrotechnic devices. Each have to work perfectly. One critical wire short, or one key thing, mechanism that doesn't work or breaks, and it's mission over. And so it's, and it's very easy. We're human beings. We're not perfect. Mistakes can be made. We count on each other to find our own mistakes, and we work very hard to learn from the mistakes of the past. We've had many failures. Remind people, roughly around half of the missions to Mars over history have failed. And so that could happen today too. Even though we've had a nice, wonderful string of successes in the United States, it's still still a bit of a gamble that we have hoped that we have erred in the side of luck, and we've stacked the deck and loaded the dice to make this thing succeed. But if we do fail, and something bad happens today, I can tell you we're going to learn it. We'll have the data that tell us what happened. We'll know why. We'll figure it out, and if we are allowed, we will pick ourselves up and get us back on the horse. And if Congress and NASA allow, we will try again. As we always do, we will learn from our mistakes.
And what are the possible scenarios we could be looking at today?
Well, there's things like one of the key stressful elements for all of us is parachute inflation. But just even separating from the cruise stage is a pretty major event. Lots of devices have to work properly. certainly the heat shield separation, getting the descent engine started. There's no less than 16 rocket motors that have to work. 8 to control during entry, another 8 to control it during landing. I said it's a lot of stuff, and it all has to work. And guess what? We haven't done this before with this vehicle ever. This is its first attempt to actually land. We can't try this on Earth. We can't do. We don't have test pilots to try it out on this planet before the big show. So this vehicle is doing it for the first time. We've done the best testing we can do in bits and pieces, but you know, it's as best as we can do. But I think our team is up to it. This team is the best. It's a diverse, intelligent, amazing group of people. People from all over the world who worked on this, not just here in California, but all over NASA, contributors from aerospace, universities, countries around the world. It is just an incredible, remarkable engineering achievement, and I am just so proud of this team.
Thanks, Rob. Now, let's listen back into mission control.
Flight, we're about 14 minutes from entry interface. The vehicle is currently preparing the heat rejection system that has kept the thermal system cool inside the air shell for about the last 6 months. This will allow the spacecraft to more easily cut the lines in upcoming cruise stage separation, which is under 4 minutes now.
We have now enabled the Rover Pyro bus.
That's the pyrotechnic system that's
we are powering off the cruise stage devices.
And these are the things in the cruise stage that we no longer need. With the pyrotechnic system working, we can explode the devices.
The vehicle is preparing for the upcoming cruise stage separation in about 3 minutes 15 seconds by powering off all the devices on the cruise stage in order that they can be safe once the cruise stage is jettisoned.
Yeah, this cruise stage has been very reliable.
We are firing our first pyros to vent the HRS liquid and gas.
This has been the coolant that's kept our vehicle from getting too hot on the way to Mars. We have to vent it into space. And this is one of the first major events that take place as part of entry descent landing.
The HRS vent anchor is complete. We will see the next anchor in approximately 3 minutes.
Okay.
We are currently 12.5 minutes from entry interface. We are coming upon cruise stage separation in 2 minutes and 20 seconds.
What's happening now, Rob?
Okay, well, we're just waiting. The rover is completely in charge. It's doing all the things we've taught it how to do. It's all built into the software. We've tested it over and over and over again. This team has spent 24 hours a day, 7 days a week testing this thing for years. And so this is really the culmination of all that work. So this vehicle is getting ready to push that cruise stage away. Once it gets pushed away, the entry system with the rover inside, with the rover still in charge, is going to get ready to take the vehicle, turn it to the right orientation, and aim it to Mars, and prepare for entering the atmosphere. This won't be long. Be prepared for this event.
We're about 1.5 minutes from cruise stage separation, about 11 minutes 20 seconds from entry interface.
Okay, so it's about 10 minutes from cruise stage separation until entering the top of the atmosphere. From then on and out, things happen fast.
We are switching to MFSK tones. Telemetry will have stopped.
Telecom is confirming that the spacecraft has switched to broadcasting tones. These tones are received directly from Perseverance, but have very limited information content. We won't receive real-time information until about 9-10 minutes from now, once the Mars Reconnaissance Orbiter starts relaying information from Perseverance. We are under a minute from cruise stage separation, about 10.5 minutes from entry interface.
It's getting exciting. I have to admit, I am quite anxious, but very hopeful that this machine is going to do what we asked it to do.
We are seeing the heartbeat tones.
Okay, that means that there's no more ones and zeros coming. It's just the vehicle telling us it's still alive.
We're continuing to receive tones from Perseverance, standing by for cruise stage separation. We have indication that cruise stage separation has been confirmed by the spacecraft.
We're off on a good start.
In about 1 minute, Perseverance's landing software will wake up and begin the final preparations for entry. The first action it will do is to fire warm-up pulses with the entry thrusters. These pulses ensure that the spacecraft gets the thrust that it wants during entry interface. We're about 9 minutes from entry interface.
Okay, so now the vehicle's on its own. It's turning itself into the direction of facing the heat shield toward Mars, and will eventually hitting the top of the atmosphere. We're not far away. This is going to go very quickly from here on out.
That's confirmation that we got shadowed by the cruise stage as it passed through our beam to the Earth.
Telecom indicated actually that we could see a signal that the cruise stage went between the Perseverance entry capsule and Earth. So we saw a little blip, the data stream indicating the cruise stage separation. We have confirmation that the vehicle has started warming up those entry thrusters. Warm-up pulses have begun. At this point, the spacecraft is trying to stop its spin from the cruise 2 revolutions per minute down to 0, and then will turn to its desired orientation from entry. It will separate the 2 balance masses that has kept it balanced during all of cruise. This will allow the entry capsule to have lift when it enters the atmosphere. We have confirmation that the spacecraft has turned to the desired entry attitude. We're about 7.5 minutes from entry interface.
Okay, the vehicle is pointed in the right direction. The thrusters are warmed up and doing their job. And now we've spun down from the 2 revolutions per minute that the vehicle had the whole way to Mars as a spin-stabilized spacecraft. And then from here on out, it's going to just be a bullet, and it's going to control its orientation and attitude via rockets on the back of that back shell.
Points carrier lock. The DTE from Radio Science from Green Bank reports carrier lock. You see the carrier on the downlink.
Flight level 1.
We are continuing to wait for entry interface. We're about 6 minutes and 45 seconds from entry interface. We have confirmation from Greenback that they are receiving direct-to-Earth telemetry via that path. The spacecraft Perseverance is currently transmitting heartbeat tones. These tones indicate that Perseverance is operating normally and has nothing significant to report. This is as expected. We're currently just over 6 minutes from entry interface.
Okay, and now we wait. As soon as we get to the top of the atmosphere, it will be very quickly, which is the entry point. It won't be very long before the atmosphere will start getting thicker and thicker. It's going very quickly at a fairly steep angle of 15 degrees into the atmosphere, and as it starts to slow down.
We're just under, we're about 5.5 minutes from entry interface. We're still receiving heartbeat tones. We expect to continue receiving heartbeat tones until about 5 minutes after entry. At that time, Perseverance will be no longer in view of our antennas here on Earth. About 90 seconds prior to entry, the Mars Reconnaissance Orbiter should begin receiving telemetry from Perseverance and streaming it to Earth in near real time. There are a few expected short outages, such as when we have a plasma blackout or when we enter the peak heating phase. Aside from these outages caused by the plasma blackout, antenna switching, or high dynamic events, spacecraft events, we should have telemetry until about 90 seconds after landing. A plasma blackout is when the signal from Perseverance isn't strong enough to make it through the superheated, super fast air flowing around the spacecraft all the way down to Earth. Once the temperature drops below that peak heating, we do reacquire the signal from Perseverance. We are currently about 4.5 minutes from entry interface. Perseverance continues to report heartbeat tones, indicating everything is nominal.
Okay, what we're looking for now is Mars Reconnaissance Orbiter should be in view soon of our vehicle and be able to listen to ones and zeros coming from a separate radio that's really designed to talk between spacecraft.
MRO reports the electro radio is powered on, ready to receive signals from the lander.
Okay, MRO is ready and able and waiting for to hear from our rover.
Mars Reconnaissance Orbiter has reported that it's ready to receive the signals from Perseverance. It should be in a few minutes here. We're just
Flight Local 1
from entry interface.
We don't need these ones and zeros, as Swati said, but to land safely, but we really need it for our own health and well-being today to keep our nerves under control. But
around this time, a second spacecraft, Maven, should begin picking up telemetry from Perseverance and will continue to record that telemetry until several minutes post-landing. We won't get that data for several hours after landing as it's being recorded and then will be forwarded to Earth later. We are continuing to receive heartbeat tones, indicating that everything is nominal. We're currently at about 3 minutes until entry interface.
Okay. Very soon we'll be getting ones and zeros, I hope, from our radio on the rover. The entry interface is nothing more than just an arbitrary place in the sky that we've defined to be above the atmosphere. But from that point on, there's definitely atmosphere, and above it there isn't.
We are 2 minutes from entry interface. Perseverance is to transmit heartbeat tones, indicating everything is nominal.
So the tones can tell us whether something's bad or not is happening. So far the heartbeat is doing well. So the vehicle thinks it's in good shape to land, which is a great sign.
We're just under 2 minutes from entry interface. As it gets closer to Mars, Perseverance is actually being pulled in by gravity and accelerating. By the time Perseverance reaches entry interface point, she should be going just under 5.4 kilometers per second. We're at about 90 seconds from entry interface and standing by for Mars Reconnaissance Orbiter to pick up the telemetry. We are 1 minute from entry interface.
MRO is received mode.
We have confirmation that the Reconnaissance Orbiter is now relaying data from Perseverance. We're about 30 seconds from entry interface. Perseverance is going about 5.2 kilometers per second and is about 190 kilometers altitude above the surface of Mars.
Confirm your data flow.
About seconds from entry interface. 5.3 kilometers per second and an altitude of 150 kilometers from the surface of Mars. We have confirmation of entry interface. Perseverance is currently going 5.3 kilometers per second at an altitude of about 120 kilometers from the surface of Mars. The spacecraft is now waiting until it begins feeling the atmosphere of Mars slow it down. Once there is enough atmosphere, it will start controlling its path to the landing target. Navigation is also confirming that we can see a little bit of that slowdown of the atmosphere on the Perseverance entry capsule. Our current velocity is about 5.36 kilometers per second and an altitude of about 67 kilometers from the surface.
We are probably seeing MRO plasma blackout at this point.
The vehicle should be doing its turns right now.
MRO has lost lock.
Perseverance. We have indications that Perseverance is now performing bank reversals in the atmosphere. These are the steps in order to control its distance to the landing target. Perseverance has just passed through the point of maximum deceleration and has indicated that it felt approximately 10 Earth Gs of deceleration.
MRO has lock again.
We saw a small outage of the UHF telemetry from Mars Reconnaissance Orbiter during that peak heating phase, likely caused by the plasma blackout. Perseverance is still continuing to perform bank reversals in the atmosphere to control its distance to the landing target. Perseverance is going about 1 kilometers per second at an altitude of about 16 kilometers from the surface of Mars. We have entered heading alignment, which means Perseverance is no longer trying to control the distance to Mars, but to the target on Mars, but instead is flying straight to the target. Our current velocity is about 550 meters per second at an altitude of about 15 kilometers from the surface.
MRO is reporting good telemetry log.
We are coming upon the straighten up. We are starting the straighten up and fly right maneuver, where the spacecraft will jettison the entry balance masses in preparation for parachute deploy and to roll over to give the radar a better look at the ground. The navigation has confirmed that the parachute has deployed and we are seeing significant deceleration in the velocity. Our current velocity is 440 meters per second at an altitude of about 12 kilometers from the surface of Mars. Perseverance is now slowed to subsonic speeds and the heat shield has been separated. This allows both the radar and the cameras to get their first look at the surface. Current velocity is 145 meters per second at an altitude of about 9.5 kilometers above the surface.
Yes, yes, yes.
Perserverance now has radar lock on the ground. Current velocity is about 100 meters per second, 6.6 kilometers above the surface. Perseverance is continuing to descend on the parachute. We are coming up on the initialization of terrain relative navigation and subsequently the priming of the landing engines. Our current velocity is about 90 meters per second at an altitude of 4.2 kilometers.
Almost there.
We have confirmation that the lander vision system has produced a valid solution and part of terrain relative navigation. We have priming of the landing engines. Current velocity is 83 meters per second at about 2.6 kilometers from the surface of Mars. We have confirmation that the back shell has separated. We are currently performing the divert maneuver. Current velocity is about 75 meters per second at an altitude of about a kilometer off the surface of Mars.
TRN Safety Bravo.
We have completed our terrain relative navigation. Current speed is about 30 meters per second, altitude of about 300 meters off the surface of Mars. We have started our constant velocity accordion, which means we are conducting the sky crane, about to conduct the sky crane maneuver.
We've lost direct to Earth tones.
As expected. As expected.
Sky crane maneuver has started. About 20 meters off the surface.
We're getting signals from MRO.
UHF is good. Touchdown confirmed. Perseverance safely on the surface of Mars, ready to begin seeking the signs of past life. At this point, the descent stage has flown away to a safe distance. Perseverance is continuing to transmit direct through Mars Reconnaissance Orbiter to Earth.
Oh my God. Oh. Oh.
MRO reports they're still getting telemetry from the lander.
All right, all stations.
We got it.
Touchdown confirmed. We're going to wait for the images.
Wow.
This is so exciting. The team is beside themselves. It's so surreal. Stay tuned. We might get some pictures.
That'd be great.
So much has been riding on this.
Yeah, we just heard the news that Perseverance is alive on the surface of Mars.
It's not
Flight, we have seen the completion of EDL 3000. Copy activity. That is as expected.
MRO is still seeing a strong signal from the lander.
We have just heard the news that Perseverance is alive on the surface of Mars. Congratulations to the mission. And looks like we have some more news in. It looks like we're getting the first image. Here, take a look at the first image.
Flight, this is OL3. I have the target point on the map when you are ready.
We are ready, OL3. Go for it.
Flight, I'll be moving in, showing you the safe zone that we've landed in.
Just put the first image from Perseverance on the surface of Mars. Now it comes from the engineering cameras known as the hazard camera. This camera is mainly used to help the rover drive safely around Mars, and we will get higher resolution photos later in the day.
Look at that, right? You get the safe.
Wow, that's the orange. Nice. This is amazing.
Here's Andrew.
For Steve. Stand by for Steve.
You did it. You did it. You did. You led the team. You made it happen, man. Congratulations, Jordan.
We just got our second image in. Our second image is in.
Okay, these we have a camera in the front and rear of the spacecraft. They're near the ground, so these are pretty close. So you can see the wheels there, and they're a little dirty because we've got glass covers over these cameras. But we took these seconds after landing, so there's still dust in the air from our landing event. So this is happening. This happened just seconds ago. Just arrived, and this is really amazing. And we even know where we landed. This is the most amazing thing. The vehicle has told us where it's landed because it figured it out. This is a sign. NASA works. NASA works. And when we put our arms together and our hands together and our brains together, we can succeed. This is what NASA does. This is what we can do as a country. On all of the problems we have, we need to work together to do these kinds of things and make success happen.